All right, guys. Lesson 4-2. Just as a quick reminder, 4-1 was actually where we introduced Newton's first and second laws of motion. All right. Today we're actually going to introduce and establish an understanding for Newton's third law of motion. And then we're going to try to come to understand weight as a force and the existence of what we call the normal force. All right. Now, to get started, Newton's second law, as a quick reminder, allowed us to describe quantitatively how forces affect motion. But in this lesson where we introduce Newton's third law of motion, we ask the question, where does force come from? Where does force come from? Okay, so based off of all observations we can make, force that is exerted onto any object must have been exerted by another object, okay? This is always true. Even gravity is being exerted by an object. In our case, Earth, okay? Every type of force must be exerted by another object. So I want us to consider this scenario where we actually have a hammer and we're driving a nail into wood, okay? So we have the image here. Considering the act of driving a nail into wood with a hammer, I imagine most of us in here have at least done this or seen it done, at least on TV, okay? What happens is you're using the hammer and you're striking the head of a nail with the goal of applying enough force onto the head of the nail to move the nail into the wood. Do you guys agree with this? Yeah, so in that motion, what happens is that the hammer also stops moving. You can imagine, correct? Okay, so what force is causing the hammer to stop moving? Go ahead. That's a good guess. That's a really good guess. It's something similar to the normal force. It's not exactly the normal force because we're going to introduce what the normal force is a little bit later. But it is similar to the normal force in that it is the force that is moving in the opposite direction to the force from the hammer onto the nail. Okay, so what I'm saying here is that while the force of the hammer does cause some motion in the nail, hopefully, okay, the nail also applies some force to the hammer, a lot of force, enough to make it stop almost immediately, right? As soon as the hammer makes contact with the nail, the hammer's not going to move that much farther. It will move the nail some, but it is very, very quickly decelerated down to a velocity of 0. Do you agree? So where does all that force come from? That force comes from the nail. And how much force is it? Well, it's equal to the force that was applied from the hammer. Okay, it's equal, but in the opposite direction. All right, and this is how we come to Newton's third law of motion, which is, here in red is kind of the textbook definition. Whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction onto the first. Kind of what you've probably heard before is, for every action, there's an equal and opposite reaction. That's exactly what we're referring to right here. Make sense? Awesome. So, now that we've introduced this law, we can talk about how rockets work really quickly. I don't know if anybody's ever wondered, okay? That fire, or what looks like fire, that's being expelled out the bottom of the rocket, okay? That is being expelled out of the bottom of the rocket with a lot of force. And all of that force being applied to those particles to shove them out the back of the rocket is being equally applied in the opposite direction by the particles onto the bottom of the rocket, causing it to move upward. So whether or not this rocket is near the ground or not, you're going to have the same result. If the rocket was in space and shot out those gases in the opposite direction, it would still move forward. Because what's happening here is that it's not pushing off of the ground with this, okay? It is expelling those gases, and the gas particles themselves are forcing the rocket upward. Does that make sense now that we've established Newton's third law? Awesome, awesome. So, I'm going to skip past this image really quick. I'm going to come to the concept of weight. Now, it's important that you understand that weight, especially in physics courses, is a force, okay? It's not mass. Weight is how much force you apply downward due to the acceleration due to gravity, also with respect to your mass. So what I'm saying is that we're going to follow Newton's second law, which is F is equal to ma. But in this case, if we're talking about weight, we're talking about your mass, and we're talking about the acceleration due to gravity. Okay? So weight, one more time, is basically the force due to gravity that your mass creates. Okay? So then what I'm saying is that at least in this Physics 1 class, our units that we're going to be using for weight are newtons and not a unit for mass like kilograms. Right? Because our weight, again, is force. And the way that we would get our weight is if we knew our mass and what the acceleration due to gravity is, the product is our weight. Have I made that clear? Good. It just follows Newton's second law. So you'll notice the way that I've written Newton's second law here is I have my force vector with a subscript of g to represent that this is the force due to gravity, also known as weight. And I'm setting it equal to some lowercase m, which represents mass, and then a lowercase g vector, which we should all come to understand as acceleration due to gravity, which is usually 9.8 meters per second squared. Agreed? Awesome. So look at the blue text. But wait, based on what we just learned about Newton's third law, if our weight is a constant force downward, what is causing us not to sink all the way down to the center of the earth? The ground, sure. So if we are not experiencing acceleration, then we must not have a net force. Do you guys remember this? All right, so right now, I am experiencing a force due to gravity because acceleration due to gravity is always acting on us. The force of gravity is always acting on us, okay? But I'm not moving. I do have a force downward. If I stepped on a scale, I can measure my force downward. But why am I not moving?
The building is pushing back up at you with an equal force?
Exactly. The ground is pushing up with an equal force to match my force due to gravity. Okay, this is always happening when an object within a gravitational field is at rest. Okay? And that force in direct opposition to gravity, which is always equal to the force due to gravity, is what we call the normal force. We can always calculate the magnitude of the normal force simply by calculating your force due to gravity. Consider this statue of Abe Lincoln. Let's say we know the mass of Abe Lincoln here. And we know the acceleration due to gravity, 9.8 meters per second squared. We could find how much force downward due to gravity this statue is applying to the table. That would be equal to the normal force, but the normal force in this case would be directly upward in the opposite direction. Make sense, guys? All right, so you know how to calculate normal force now. It's just force due to gravity, but it's opposing gravity in its direction. All right, to cap off this brief lecture, let's talk about what is happening to this box. All right, let's assume that it is close to Earth, okay? And it's currently experiencing a force due to gravity of 98.0 newtons. At the same time, it's experiencing a force upward of 100 newtons. Can somebody tell me what its net force is? Go ahead. 2 newtons upward. So there is a net force. So then my next question is this box accelerating? I see a lot of heads nodding up and down, yeah. It is accelerating, absolutely, okay? So then if the question is simply what happens to the box in this scenario, I think a simple answer could just be it's accelerating upward, right? And that would be good, you could write that, and that's probably like worth 1 point on the AP test. But do we have enough information to find out by how much it's accelerating? I see a lot of head nods. All right. Can somebody tell me what is the first step I might want to take if my goal is to find out the actual magnitude of acceleration? Go ahead.
Find the mass.
I could find the mass. You're absolutely right. How would I go about doing that?
Since the force of gravity is equal to mass times the acceleration of gravity, 98 is equal to mass times 9.2.
All right, I'm going to go ahead and write down what you just said. You tell me if I'm wrong, okay? You said that the force due to gravity, which in this case is equal to 98.0 newtons, should and can be set equal to m for mass times 9.8 meters per second squared for acceleration. Is that what you're saying?
Yeah.
All right, cool. And then just one quick algebra step later, I can divide 98 newtons by 9.8 meters per second squared, correct? That would give me what? 10, what are my units? Not 100% sure? That's all right. I'll tell you now that it's kilograms, and I'll show you why. 10 kilograms is equal to my mass, and the reason that I know that is because in our previous lesson, we established that the actual units that we're using when we're talking about newtons are kilogram times meters per second squared. So if you divide this by a meters per second squared, all right, we're canceling out those meters per second squared, and all we're going to be left with is kilograms. Sounds good? All right. Now, we now know that the mass of this object is 10 kilograms. What would be the next step in order to find the magnitude of its current acceleration? Go ahead.
So we know the force upwards, which is 2 newtons, and we also know the mass, which is 10 kilograms. All we have to figure out is the acceleration, and since we know F equals ma, we can plug in the 2 and the 10, and just simplify. So 2 is equal to 10 times the acceleration, so 2 divided by 10.
That's exactly right. All right, so for those of you that may not have heard, I'm going to go ahead and do exactly what you just told me in math on the board. You tell me if I made a mistake, okay? All right, so you're saying that we could just take the general form of Newton's second law, F is equal to ma, and we can say that we know that the net force that the box is experiencing right now is 2 newtons. So I could say 2 newtons is equal to, we know the mass of the box that is moving, 10 kilograms. And then there's just one missing variable, so we can solve for a. Is that correct? All right. So then one algebraic step, divide both sides by 10 kilograms. All right. I divide 2 newtons by 10 kilograms. What units do I get when I make this division? Meters per second squared. Is that a reasonable set of units for acceleration? Absolutely. All right. So 2 over 10. How can I simplify this?
1 over 5 or 0.2.
1 over 5 or 0.2. All right. I'm going to say 1/5 meters per second squared. Are you guys happy with this? All right. Is equal to our acceleration. All right. So now, if the question was, what happens to the box in this scenario? We can say, well, it's actually being accelerated upward at 0.2 or 1/5 meters per second squared. All right. That's a lot more information. All right. That's a lot more information. Fantastic. That's it, guys. Can you press pause on the recording?